This is learning objective number 2. We're going to talk about periodicity, what we mean when we say that are trends in the periodic table. We're only going to look at 3 of these. Is size, and this is the diameter or the radius, the radii of the atoms. So we're going to look at atomic radii and see what the trends are. The second one is electronegativity, and that is a tendency for an atom to attract electrons. All atoms attract electrons. The question is how well they do it. And then finally, is ionization energy, and the ionization energy is the energy required to remove an electron. And so to talk about this, we're going to go back to our electron configuration. So here's the periodic table that I just pulled up, and we will note that the size increases as we go across the periodic table this way and down. Okay, and so size increases as you go this way and down. And what we want to do is figure out why that does, because if you can understand that, it'll make it easier to memorize. So we're going to look at the second row here, and we're going to talk about electron configuration. So that is from last semester. Let's start with hydrogen, helium, lithium, and beryllium. Hydrogen is a 1s with 1. Helium is a 1s with 2. This is n equal 1, and it's the first shell. And that's the concept. In this row, we have a shell. Okay? Now we're going to talk about this shell in this second row on it. So when I think about this, you should have your periodic table out. I have my nucleus here, and I have my shell, and helium has 2 electrons moving around in this shell, and it has 2 protons. 2 protons, each with a +1, and 2 electrons with a -1, and they cancel each other. That's what I have when I go in the first row right here, and helium over here. Now when I go to the second row, on this row, I start filling up the second shell. Okay, so for the second shell, I start with lithium, and I have 1s2, 2s1, and so my lithium consists of my nuclei with 3 protons, and I have my first shell in here with 2 electrons, and my second shell out here with 1 electron. And so what I can envision is these 2 electrons cancel 2 of the positive charges. So if I was to draw a positive, positive, positive in my nucleus, I'd have a negative here and a negative out here, and they're all in this shell, and they're going to cancel 2 of these positive charges. My second shell, I'll have 1 negative charge, and so this electron out here will essentially see 1 positive charge. And so that's the attraction for the shell. It's 1 electron seeing 1 positive charge. Now what happens when I go to the next element, beryllium, right here, okay? Here we go with beryllium. It's 1s2, 2s2. And so I have the same thing as before. I have my nucleus with 4, this time 4 positive charges. There's my nucleus. I have the 1s2, and I have the 2s2, and these electrons are spaced out here. I probably drew these too close together. They avoid each other. They're in this area somewhere. 2 protons cancel 2 electrons. 2 protons, 2 electrons. And then I have, on the outer shell, I have 2 electrons and they're seeing the two protons that are left. So in the outer shell, I have 2 protons, and I have 2 electrons being attracted to them. So as you know, opposites attract, and so I have essentially a +2 attracting each electron. And that is a strong attraction, and so since it's stronger than before I had 1 electron being attracted to 1 proton. So here I have 1 electron. Each electron is attracted to 2 protons, and so it shrinks that shell. And you can see what's going to happen. If I go to the next element, and I'm not going to move my periodic table, let's jump up to carbon. Carbon is 1s2, 2s2, 2p2. And so here's my nucleus. It has 6 protons. And so here they are, plus, 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 plus. And I have 2 electrons out here in this shell. Again, here I'm going to draw it better this time. 1 there and 1 there. That's this shell. And then on my outer shell, I have 1, 2, 3, 4 electrons left. So here they are. I should put it in black. 1, 2, 3, 4, all scattered about, moving about, and they're all attracted. So I have canceled 2 of these. And so I have, and those 2 are canceled by this electron and this electron. And so now I have a charge of 4 in the center. I get a +4 because I have 4 protons left, and each electron, I have 4 electrons, -1, -1, -1, -1, all being attracted to that +4. And so each one of these sees a +4 charge. And so this shell shrinks down. I can't draw it shrunk. It actually looks the opposite because I put more in there, but it actually shrinks down because I have bigger charge. And this goes the whole way across. If I go over to fluorine, we'll do it. It is 1s2, 2s2, 2p5. So 1s2, 2s2, 2p5. And so once again, we're going to have, in the center, we're going to have 1, 2, 3, 4, 1, 2, 3, 4, 5. That's a total of 9 electrons. That makes it bigger, but it doesn't change size. Again, we'll have our first shell with 2 electrons in it, drawn here, and we have 2 protons being canceled. I'll cancel them out right here, and that's our first shell, like that. We'll put our second shell in, which I draw bigger, but it's actually the opposite way, because now I have 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7 protons. So I have a +7, and I have 7 leftover electrons up here that are out here on this shell, and so each 3, 4, 5, 6, 7, and so each electron sees a +7 charge in the middle, and so it's sucked in really, really small. And of course this all looks backwards because I had to put more and more stuff in there. But you get the idea. And so what you see then, if I drew them correctly, and I'll do that now, we have a nucleus like this. Here's our first shell, and that's always the same here. And then here we go for lithium. We only have 1 electron. Then as we go across, if I jump over to carbon, I have my shell, and I got this one being sucked in, and then it goes like that, because here I had one electron, now I have 1, 2, 3, 4 electrons being sucked in with a +4 charge. And then fluorine, which is way over here. There's my there's my nucleus right here. Here's my first shell right here. Here's my second shell, and it's being sucked in even more because I have 7 plus charges and 2, 3, 4, 5, 6, 7 electrons around it. We see as we go across the periodic table this way, the size decreases all the way through to neon. If I go back up to my periodic table, we've gone the whole way across here. When I go to sodium, I jump to the third shell, and so it gets bigger all of a sudden. So on sodium, I end up with this. Here's my nucleus, my first shell, my second shell, and then we go out here to the third shell. And so as you go down the periodic table, it gets bigger. So the size goes like this. The size decreases in this direction, up and over. And that controls everything. So now it becomes easy. Let's talk about electronegativity. Electronegativity increases as we go up the periodic table and over. So if I go back to the periodic table, back here somewhere, we see electronegativity. We will see electronegativity increasing as you go this way, up and over. And so we expect fluorine to be the most electronegative, then oxygen is next, and nitrogen, then chlorine. Chlorine and nitrogen are about the same. And so you'll, in general, as you go up and over, the electronegativity increases. One of the reasons you can use is the size decreasing because it's attracting more and more electrons closer to the nucleus. It's the same type of reasoning as we just went through. So electronegativity does that, and ionization energy, I hope you can figure this out. That's the energy needed to remove an electron. Well, if you're attracting, if my shells are being attracted more and more strongly as I go across the periodic table, it's going to be harder and harder to remove an electron. So in general, the ionization energy is going to increase as you go across the periodic table and up. So electronegativity and ionization energy, i.e. and electronegativity, increase as you go up and over. Size does the opposite. Size increases as you go to the left and down. That's what you have to know and what you have to understand. On the exam, I'll ask things like multiple choice, which is more electronegative, which has a higher ionization energy. Understand, for the ionization energy, there's a few exceptions that I'm not going to ask. They occur between this row and this row, and they occur here. It's an exception when you go change from nitrogen to oxygen, phosphorus to sulfur, arsenic to selenium, and you have an exception when you go beryllium to boron, magnesium, or calcium to gallium. We're never going to deal with these. You don't have to worry about ionizations or electronegativity on those. You'll see some changes there. That's it for this outcome.